So now I'm going to be talking about another important article for entity linking. We use a dual encoder and we apply it for biomedical text to do entity linking. But this approach is fast and effective because we are working at text level instead of just mention, then another mention, then another mention. And we will see at the last slide, I will show you that this approach is very fast because it deals with all of the end mentions all at once, so it's fast. And so I want to focus on this important article in 2021. So the motivation is that they have two main motivations. And recent advancements in entity linking using BERT-based models follow a retrieve and re-rank paradigm, where the candidates entities are first selected, first retrieved, and then the candidates are ranked by a re-ranker model. So while this paradigm produces state-of-the-art results, they are slow, both at training and testing time, as they can process only one mention at a time. Processing one mention at a time incurs a substantial overhead both during training and test time, leading to a system that is slow and impractical. So our idea should be practical, our algorithm should be scalable, So they propose a BERT-based dual encoder model that resolves multiple mentions in a document in one shot. We show that our proposed model is multiple times faster than existing BERT-based models while being competitive in accuracy for biomedical entity linking. Additionally, we modify our dual encoder model for end-to-end biomedical entity linking that performs both mention span detection and entity disambiguation. So we propose a collective entity linking that processes an entire document all at once, instead of just mention with mention and then another mention. So such that all entity mentioned within it are linked to their respective target entities in knowledge base in one pass. B-Link deploys two separately trainable models for candidate retrieval and re-ranking. In contrast, our method learns a single model that can perform both retrieval and re-ranking steps of entity linking. So biomedical texts are really challenging, and they contain substantial domain-specific jargon and abbreviation. For example, CT stands for copper toxicosis or computed tomography. And also, the target concepts in the knowledge base often have very similar surface forms, making disambiguation task difficult. For example, this one is a kind of bacteria, but the same surface form, of course, adding another token infection is a disease. So by adding another token number 3, it becomes a disease. It's not a bacteria anymore. So it's very delicate, I say. The contributions is that the training our collective entire disambiguation model is 3 times faster than other dual encoder models with the same number of parameters that perform per mention entity disambiguation. At the same time, our model obtains favorable results on 2 biomedical datasets. And our model can also perform end-to-end entity linking when trained with the multitask objective of mention, span detection, and entity disambiguation. So they show that without using any semantic type information, their model significantly outperforms 2 recent biomedical entity linking model, MedType and size space. So this is a token candidate entity A1, A2, And because it's a classification, we have CLS, and also we separate all things in the context because it's mention and context. And so we have mentions with context. For example, this is a mention, this is another mention. So here it's not just one mention. We have identified all of the mentions, all two of them, CF and CFTR. And then here we have candidate entities for each mention. And the rest of that is standard. We use dot product and we get the score to link mention to entity. So given a document X1, XT of T tokens, so we have one document, but we have T tokens with N mentions. It's not just one mention. We have N mentions and a set of M entities in a target knowledge base of E. So the task of collective entity disambiguation consists in mapping each entity mention M sub K in the document to a target entity type sub K in one shot. Each mention in a document may span over one or multiple tokens denoted per ing. And you will see that they have an interesting trick that they limit. Because the number of spans, the combinatorics becomes huge, so they have a clever idea. I mean, they say they limit the size of the span. For example, they don't go more than 4 tokens, a sequence of 4 tokens. They don't go more. So it's not, so it's I can say it's a heuristic that they will use it. So their model consists of 2 BERT-based encoders. The mention encoder is responsible for learning representations of contextual mentions, and the candidate encoder learns representation for the candidate entities. And so CLS and then separator, they use it for start, and they use start and end special tokens. Because for example, HI is the start of the mention, HJ is the end of the mention, and so after you represent it, you have a sequence of H1, H2, HT, because we have T tokens. But for example, if your span starts from HI till HJ, so this is the span of your mention, we only take the first one and the last one. Then we concatenate it here, goes to a linear layer with bias. And then, so this is a representation of mention K only. For candidate encoder, given an input candidate entity, E, is a sequence of tokens, T tokens. The output of the final layer corresponding to CLS token yields the representation for candidate entity. So, and you know, this stands for classification in BERT is standard. So for a candidate retrieval, since the entity disambiguation is formulated as a learning to rank problem, we need to retrieve negative candidate entities for ranking during training. So they sample a set of negative candidates from a pool of entities in the knowledge base. And for candidate scoring, the retrieved set of candidate entities, these retrieved for each mention, are scored using this dot product between the mention representation and its candidate representation. So this is a score of your candidate C. And for loss function in training, they train their model using cross-entropy loss to maximize the score of goal target entities. And for inference, we do not require candidate retrieval per mention. This is the gain that we get. The representations of all entities in the knowledge base can be pre-computed and cached. So the inference task is thus reduced to find the maximum dot product between each mentioned representations and all entity representations. So for mention span detection, they calculate the probability of each candidate mention As I said, spans starts from I till J, but there are something in the middle as well. But we're represented from different, we learned another parameters as well, so that it becomes significant and expressive. So entity disambiguation, we represent each entity I till J, because it's a span from I till J, by mean pooling. Because we need just one vector, we cannot say we have a sequence of vectors, so it's a simple trick that we use mean pooling. Mean pooling is the simplest form of pooling. And during inference, they choose only the candidate mentions with probability above the threshold as a predicted mention spans. And they use these two data sets, med mentions and BC5 CDR. Med mentions has more mentions, 300,000, and more types, 128 types. And the results, as you see, we still have low precision and recall and F1 score, so we can still write an article to outperform these state-of-the-art models. But what is significant in this paper is that they have done it very fast, because instead of just one mention, we do all mentions at once, we train all mentions at once, and going from one mention to another mention is too slow. So you see that it takes more time. This red one is just one mention. You see it takes more time. It takes around more than 1,250 minutes. But this one ends at less than 1,200.